The invisible balance. Bridging boundaries and surfaces through the Generalized Curl Theorem. The story of the Generalized Curl Theorem is one of hidden symmetry, a mathematical bridge that links the behavior of a function along a simple closed loop to the twist of that function across any surface capped by that loop. This sheet explores how we move from a theoretical proof to a visual confirmation that this balance remains perfect, regardless of how complex the landscape becomes. The bridge. From known laws to new identities. Our journey begins with a well-established law of physics and math. The standard theorem that relates the swirl of a force field to its flow around a boundary. To prove a more generalized version of this, we perform a conceptual stress test. We imagine a simple field constructed from a single value that changes in space, multiplied by a constant direction. By applying the standard rules of swirling fields to this setup, we discover a remarkable identity. The sum of a function's values along a path is exactly balanced by a specific kind of curl-like derivative spread across the surface. The first demonstration. The smooth hemisphere. To see this in action, imagine a perfect hemispherical dome sitting on a circular base. We choose a mathematical function where the values change smoothly across the dome. In this first test, we calculate two things: the effort of the function as we travel around the red circular boundary, and the sum of the twist components, visualized as tiny blue needles, across the blue surface of the dome. Even though these two calculations look entirely different, the results converge to the same value, proving that the twist on the surface perfectly balances the flow on the rim. The stress test. The rippled bowl. One might wonder, does this balance only exist because the dome is smooth? To find out, we replace the hemisphere with a rippled bowl, a jagged, complex surface that rises and falls unevenly. We also swap our simple function for a much more volatile one, where values oscillate and grow rapidly in every direction. This forces the needles of the surface integral to change direction and intensity at every point. Remarkably, the theorem holds. The jaggedness of the surface and the complexity of the function do not break the connection. The total sum across the rippled landscape still matches the boundary line exactly. The grand finale. Topological independence. The final realization comes when we view these two surfaces side by side in a dynamic animation. Whether the surface is a smooth dome or a distorted, rippled bowl, as long as they share the same circular boundary, the total twist across them remains identical. This demonstrates the projection principle. The theorem effectively takes a complex 3D interaction and projects it onto a specific axis. It proves that the generalized curl theorem is a fundamental property of space itself. It tells us that the interior geometry, no matter how complicated or noisy, is always strictly governed by the values living on the edge.